equivalent circuit of induction motor. So this is the equivalent circuit of a stator. So you are going to give a supply. Windings will have a resistance and reactance. You will have an induced EMF. An induced EMF will oppose your source. So you have this EMF is opposing your source V1. So this is the equivalent circuit of your stator. If you see the rotor, you will have an EMF induced E2. You will have a resistance and reactance JX2, and the rotor frequency will be FR equal to S into F. And I'm in case if I'm going to the motor is running on full load, means the current will be very heavy, so I can short circuit the rotor terminals. And between the rotor and stator, see here the coupling is provided by the flux. E1 and E2 are coupled by phi. This phi is going to be the flux due to the rotating air gap magnetic flux. So stator and rotor will have an air gap in between them, right? So through that air gap, you will have coupling happening between the stator and rotor, and that coupling is through electromagnetic coupling in the form of magnetic flux. So this is the just like transformer, stator is a primary, rotor is a secondary. Primary and secondary are coupled by the magnetic flux. So all these are per phase. Per phase means only for one winding. Three phase means I have to draw the diagram three times one below the other for three phases. So that finally the power will be multiplied by the value three, three times. Okay. So I can write E1 into I1 conjugate three times the power E1 into I1 conjugate will be going into the stator. EMF represents the power and the magnetic energy leaving the stator and passing into the gap. So this voltage multiplied by the current will be passing into the air gap, that will be coupling with the rotor. And finally, whatever power is absorbed in the rotor will be circulating as current I2 in the rotor circuit. So whenever we find power, we always find the real power, because real power only will be the actual power which is transmitted and lost. We will not be worrying about the reactor and the other apparent powers. We are more worried about the real power. So real power we'll be subtracting all the copper loss and other losses. Finally, whatever power is going to come out in the shaft is going to be the mechanical power. The reactive power will be used for storing the energy. Real power will be used for calculating the loss and for dissipating the energy. And in the rotor equivalent circuit, we have seen the rotor equivalent circuit and everything. See, the x2 will be multiplied by s. We have seen s into x2 naught. X2 naught means standstill. X2 means running. Even the induced EMF E2 will be S into E2 naught. E2 naught means standstill. E2 means running. So the total rotor copper loss is three times, because three phases. 3 into I2 square into R2. I2 is the rotor current. R2 is the rotor resistance. Whenever loss means, you will always take the resistance and not the inductance. Okay, so the equivalent circuit is shown previous diagram. So finally, the equivalent circuit I have shown you in this diagram, stator and rotor, they are coupled by the flux. Okay, and N1 and N2 are the rotor. N1 is the number of turns in the stator, and N2 is the number of turns in the rotor. Okay, XG will represent the air gap stay resistance. The final diagram you see here, this is the final diagram equivalent circuit of induction motor. You have, this is your stator part, this is your rotor part. Both are coupled by the air gap, and this XT is the reactance because of the air gap. So you have primary current, secondary current, and N1 is to N2 is going to be the turns ratio. Current relationship, I1 is the total current coming inside, IG is flowing to the stay reactance, and I1 is the effective current going into your stator, and I2 is the current flowing in the stator, in the rotor. E1 and E2 are the EMF induced in the primary and secondary of your stator and rotor. Turns ratio will be N1 is to S into N2. Even you have to multiply the turns ratio by S. Okay, current means I won't do that. Voltage means I'll be multiplying by S. See, that is what is given in the thing. So the turns ratio, everything, the derivation is given here. E1 by E2 is N1 by S into N2. Normal transformer, S will not come, but for induction motor, this S will come. And rotor current, we have seen the expression I2 equal to E2 by Z2. Z2 is R2 plus J into S into X2 naught. So see here, this is how we relate induction motor with the transformer. You have a stator, till this portion stator, here ideal transformer, then rotor plus mechanical vibration. So this is the equivalent circuit of induction motor combining the case of an ideal transformer. So see here everywhere, if you keep the turns ratio to be without S means everywhere you have to divide by S. If you keep the turns ratio as S into N2 means you'll be writing the other terms as it is. So aduketa mari you have to see how you are rewriting. See here the turns ratio I have written as N1 is to N2, which means I have to divide E2 by S, I have to divide R2 by S. The turns ratio is N1 is to S and 2 means I'll be writing it as E2 and R2. Here I will have J into S into X2 naught. Either you'll be multiplying by S or you'll be dividing by S. Please understand that clearly. Okay. So the ratio we have seen previously 1 minus S by S. So that will determine the total power available in the final circuit. So it is going to be PD equal to 3. I multiply by 3 because it's 3 phase 3 into I2 square R2 into 1 minus S by S. So 1 minus S by S is going to be the R2 is going to be, it will account for the rotor electrical loss, and 1 minus S by S is going to be the developed mechanical power. If there is no slip means it will be fully converted into mechanical power, because you have the concept of slip, you will have the effect of slip everywhere in the power expression. So it is 1 minus S by S. So finally, if you include all the resistance R2 everything, and this is going to be the final equivalent circuit including all the resistance R1 and X1, stator resistance and reactance. Ri and X3 is the leakage thing. This is ideal transformer. Then you have the rotor resistance and reactance. Then you have the mechanical side of the power. So you include everything. This is the final equivalent circuit of an induction motor, which is used for calculating the developed power. Okay. And same way, see, in a transformer, we can move all the secondary components into primary side, or we can move all the primary into secondary. That transferring is possible in a transformer, right? Same way, I can do this. Since induction motor is more or like similar to a transformer, I can move all the components from stator to rotor or rotor to stator. I can draw the equivalent circuit accordingly. See here, I have moved all the components from rotor to stator. Okay, and all the components will be having a new dash notation, and you will be dividing by the turns ratio k square. Transformer use பண்ணதே concept now. We are not learning anything new. When we are going to move any component from the secondary to primary, we'll be dividing all the secondary values by k square. That is what is done here. See here, R2 dash is R2 by k square, X2 naught is X2 naught by k square. And we can simplify this using Thevenin's theorem. So as the transformer, the no load current is going to be very, very the no load current, and this thing can be ignored in a transformer, but here it cannot be ignored because this current is very, very large. It's 25 to 40% the current, right? So we cannot remove that, but if we remove, we can simplify this. The simplified equivalent circuit will be removed. If you remove this branch Ri and Xd, the remaining components will contribute to the simplified equivalent circuit of your induction motor. So I am replacing this R1 plus JX1 as ZTH. So ZTH will be the Thevenin's equivalent. You know how to apply Thevenin's theorem across AB. So apply Thevenin's theorem across this AB. You can find ZTH and Z VTH, and you can draw Thevenin's equivalent circuit diagram. So that is what is drawn here. Verify the Thevenin's values are correct. So for apply Thevenin's theorem across AB, you will find that this will be VTH and this will be ZTH. And this verifying this Thevenin's theorem, I leave it to you because we have done many problems in Thevenin's theorem. So arrive at these two answers for ZTH and VTH by applying Thevenin's theorem across A and B. Okay. and problems we'll see it later. So any doubt you have in so far whatever we have seen today, please you can unmute yourself and ask.